Today we are going to go over one of the biggest requests I've had over the last few years. How do you configure a ply number optimization for composite? So here in today's example, we're going to be dealing with a very simple cylinder with the internal pressure load. This cylinder is composed of the composite laminate that you see here on the screen. One problem with the original setup is that the failure indices for some of the elements or for some of the plies, they're actually exceeding 1.0. That's bad for us. That means the laminate is failing. What we're going to do is we're going to configure this task with Nastran Sol 200. We're going to tell Nastran's optimizer, hey, tell me how many plies do I need so the failure index is less than 1.0. One goal in this optimization is to also reduce the mass. So before we're dealing with the mass of about 4, and then by the end of this optimization, we're dealing with the mass of about 3.6. Here you get some information about what the layup is. You can see that by the end of the video, we're actually dealing with fewer layers, if you will, or fewer plies. Let me go ahead and erase some of this here. Now, there is a lot to cover in this tutorial. When you look at the tutorial file, I typically give you step-by-step instructions, but in this case, I wanted to make this video really quick, so I did not create those step-by-step instructions. What I recommend is the following. Go to the tutorial section. There you're going to find a lot of other tutorials. That's going to show you how to use the tools that we use today. Once you are familiar with these other tools, then you can follow along with this exercise. The other tutorials, I'll give you this example, this 3-bar truss. This tutorial gives you step-by-step instructions. Okay, you click this button, you type in this number, and so on and so on. This is how you run Nastran. This is how you look at the results. In this tutorial file, there's none of that. You only have this video tutorial to follow along. So I first recommend looking at the other tutorials and then looking at this tutorial. Now let's go ahead and briefly look at the problem statement. Now, when you are configuring a ply number optimization, it gets complicated. And the reason is because you're dealing with a lot of layers. If you look here, our composite actually has a core layer. We have some additional layers here, and then at the very top we have these very thin plies. There's a lot of data here that we have to connect together. There are a lot of variables we have to create. We also have to create our constraints. We have to constrain each layer. We have to make sure that the failure index is less than 1. So this is what I recommend. With any optimization, take some time, sit down with a piece of paper, a text editor, maybe PowerPoint, and create what's called the optimization problem statement. Get an idea of what your variables are and what your objective is. Is it to minimize the mass? Is it to maximize the natural frequency? Then create your constraints. What specific values do you want to constrain? Are you constraining beam stresses? Are you constraining von Mises stresses for 2D elements? Here in this case, we're dealing with a composite, so we're focused on failure indices. You could also constrain other values like ply stresses or ply strains, but in this case, I'm focusing on failure indices. Now, here on the left, I've explicitly written out what the design variables are and how they're configured. Now, on the next few slides, I'm going to talk about what the design variables are explicitly and how to recreate our ply number variables. Now, one quick thing before we go on, terminology. Now, you're going to be using words like plies, core, layers, and super plies. What do all these different words mean in regard to Nastran? Now, when you create your PCOMP entry, every row for the most part is defining a different layer in your laminate. So here, let's go ahead and write this out. So this layer is this bottom layer here at the bottom. This is going to be layer 1. this next layer, this is going to be layer 2. And you repeat the process again and again. You'll notice a few things here. Number 1, the thickness. These first few layers have a thickness of about 0.005 inches, which I believe is about 0.127 millimeters. These thickness values are the thickness values of plies. But you'll notice that the next few layers, they have a bigger thickness, 0.02 inches. So here, if you take one ply thickness, 0.005, you multiply that by 4, this gives you 0.02. So you can see that for these other thicker layers, we've actually combined multiple plies together to express one layer. So here, sometimes you'll see others refer to this as a super ply. Basically, it's an aggregate. It's a combination of multiple plies together and defined as one layer in the bulk data entry. So here, if you're new to Nastran, this is what I recommend. Call all of these rows layers. These layers could either be a ply, they could be super plies, or they could be a core layer. So again, all of these are layers, and then the second meaning could be, they could be plies, super plies, or core layers. So I wanted to clarify this because later on, you're going to be hearing me refer to these layers as either plies, super plies, or core, or sometimes I just refer to them as layers. So hopefully this helps distinguish what all these different words are. Now, when you want to perform ply number optimization, you'll most likely be working with multiple PCOMP entries. So to make this example a little bit more complicated, I also have a second PCOMP entry. It's basically identical. The first laminate or PCOMP entry is for this portion of the model. The second PCOMP entry or second laminate is for this other section of the model. Now, both laminates are identical. They have the same number of layers, the same angles, the same thicknesses, and so on and so on. I wanted to keep this example simple by using two identical laminates, but at the same time, I wanted to add some level of complexity because you are going to be dealing with multiple laminates. So I wanted to show you what the process is like when you're dealing with multiple laminates. Another thing, you are going to be working with multiple load cases. So here, this example, it's going to be dealing with 5 different load cases. So all your design constraints are going to have to deal with these 5 load cases. I also want to show you how to set that problem up. I know most tutorials are only dealing with one load case, which is very simple, but I wanted to make a very complex example. So that's why we're working with 5 load cases. And now let's briefly talk about the design variables. Now, when you are defining a PCOMP entry, there's no value here that defines the number of plies. For example, there's no value here that defines 100 plies. That doesn't exist. There's no value here that defines maybe 55 plies. The number of rows is what defines the number of plies in your laminate. So what you have here are the following. The optimizer can vary the thicknesses of the layers. That's what the optimizer can control. Also, the optimizer, if you wanted to, can control the angles, but the optimizer cannot directly modify the number of plies, if you will. It can only modify the thickness. So what we do first, we first define these thickness variables on the super plies, the layers that are super plies, if you will. So here what we do is the following. In blue is the positive 45 degree layers. In green are the negative 45 degree layers. In red are the 90 degree layers. And then in this gold color are the 0 degree layers. What we're going to do is define the following. X1 is going to be the thickness of this layer. X2 is going to be the thickness of this layer. And then we're going to repeat the process. X4 here at the top, this is going to be our thickness variables. And you can see from this diagram what we're doing. The first group of thickness variables, so this is going to be variables x1, x2, x3, x4 onto x8. This first group of variables are the thicknesses for the 45-degree layers. Our next group of layers, or variables rather, are going to be for the 90-degree layers. So here, let's go ahead and circle those layers. So x9 through x10, x11, and x12, those are the thickness variables for the 90-degree layers. And then for the last group of variables, those are going to be the thicknesses for the 0-degree layers. So let's go ahead and circle those variables. So remember, the thicknesses are what the optimizer can modify and vary. Now, once we have the thicknesses, we're going to define 3 new variables. Variables y1, y2, and y3. These variables are going to be the ply number variables, and we're going to associate these variables, these ply number variables, to the thicknesses with these expressions. We're going to say that x1, the thickness variable, is equal to the ply number variable times the thickness of 1 ply. So as an example, let's suppose that y1 at the end of the optimization is, I don't know, 100 maybe. If x8 is equal to this expression, x8 is going to be equal to 100 times 0.005. So that's going to be our thickness for x8. So remember, the optimizer cannot tell you how many rows or numbers are in this entry. It can only adjust the thickness. So what we do is we define these x variables for the thickness, and then we define these y variables for the ply number variables. So here is an explicit list of all the different relationships. I'll show you how to set this up later on in the when we're setting up the optimization actually. And then here, let's talk about the failure indices. We are not going to constrain the failure index for each layer. For the core doesn't have a failure index, so we are not going to constrain the failure index of the core. For the super plies, we are not going to constrain the failure index. So here, not for the core, not for the super plies. We are going to only constrain the results for only the ply layers or the outermost plies. Now you might be asking, why only the outermost plies? Here, let's quickly talk about how Nastran outputs results for layers, if you will. Nastran outputs results at the midplane of the layer. So as an example, here in the top in scenario A, I have about 40 plies defined for the PCOMP entry. This is what the PCOMP entry looks like. And I'm looking at the failure index output. So here we get the failure index at the midplane of each layer. So here is what the distribution looks like. Here, if we look at layer 1 here, it looks like the max failure index is about 1. Now let's look at this other example. Same loading, but the PCOMP entry only has 2 layers. Here we're using the symmetry option. Basically, we define 1 layer, and then internally Nastran creates a symmetric laminate. So technically this example has 2 layers when we use the symmetry option. Here, what Nastran does is the following. It outputs the failure index, the ply stress, the ply strain at the midplane of that layer. But guess what? Here, we get that the max failure index is about a little less than 0.3. Now, this is a problem. If we look at this configuration, we think that the max failure index is 0.3. But no, that's wrong. We know that the max failure index is a little less than 1. Maybe it's 0.98. Now, let's look at this last configuration. In this last configuration, we defined 4 layers. So we're using the symmetry option, so we only use 2 layers. We defined an outer layer. Here, the outer layer has a thickness of 0.125 millimeters, and then my core layer has a thickness of 2.375 millimeters. Look what happens here. Now the failure indices for the outer plies, they're reporting a max value of about 0.98. So here, let me briefly summarize. This configuration is not okay. This is giving me misleading results. But here, if I create these actual plies and put them at the outer regions of the laminate, then I'm getting good, reliable readings, outputs of the failure indices. The other reason why we're not constraining the interior thicknesses, this is because these thicknesses are going to change in thickness. So here, suppose at the end, it looks a little different. So maybe our core, we're actually not modifying the core. Let me jump out of here. Let me do this. Let me create a new slide here. And let me do this. Let me enlarge this. Let's suppose the optimizer creates a thicker laminate. This might influence, or actually this is not good. Let me do my best here to explain what's going on here. Let's go ahead and suppose that this layer became very small. It's very, very thin. Remember that before if we wanted to, we could track the failure index at the midplane, but when the thickness changes, this could give me different readings of the failure index or the ply stress or the ply strain. I don't want to give myself misleading results when the thickness of the layer is changing. The outer plies, those thicknesses are not going to be changing. They're going to be constant during the optimization. So it's here where I should be constraining the failure indices or the ply stresses or the ply strains. I hope this did a good job of explaining why specifically I'm only constraining the outer failure indices. If not, please feel free to contact me here at this email address here at the bottom, and I'll get back to you as soon as possible. Okay then, so a few more comments. So at the end of the optimization, if before we started off with, here we have how many layers? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 layers. At the end of the optimization, I will have 18 layers. But look what happened. The thickness of the 0 degree layer has been increased. If we look here at these fields, notice that the thickness fields have changed. Nastran is not going to add layers and remove layers. No. The optimizer can only change the thickness. So here, that's what we have. The thickness has changed. At the very end, what we're going to do is we're going to take that final super ply and we're going to slice it into individual plies. So here on the left is what the optimizer gave me as the final solution, but then at the end we are going to manually slice the PCOMP entry into different plies. So if you look at the top right hand corner, you can see what the final sliced version of the PCOMP entry looks like. So here on the left, this is what the optimizer gives me. It gives me 18 layers, and then at the end we manually slice it up into something that looks like maybe there are 40, 50, maybe 60 layers in the final result. So let me see if there's anything else. Right, we're going to go ahead and take a look at the final failure indices. Here, what I wanted to show you is what the final laminate looks like. Here you can see what the laminate looks like after we sliced it into individual plies. And then I believe at the end, we're going to look at a brief stacking sequence tutorial. So some of you might want to shuffle the plies. You have rules that you have to follow. So we'll do a stacking sequence update later on in this exercise. So I think that was the last slide before I wanted to go on. Now here, I'm here to support you. So if you have any questions on how to perform your own ply number optimization, feel free to reach me at this email address and I'll get back to you as soon as possible. Now, today we're going to be using the Soul 200 web app. Now, this web app originally started as one web application. So that would be this web app at the far left-hand corner. This web app originally was meant to let you configure tasks like a ply number optimization. But over the years, it's expanded. These days, you can perform shape optimization. You can perform machine learning optimization if you wanted to. If you wanted to optimize the ply drop-offs or the ply shapes, you can also do that. You can also look at the results. So in this exercise, we are going to be looking at the failure index results in the web browser. So this is at a big glance what the web app can do, just in case you were curious. And here, a quick comment. This is a repeat of what I mentioned a moment ago. If you want to optimize the ply shapes or where the ply drop-offs are, there are more advanced tutorials that walk you through all the steps on how to do this. Here, I'm just going through some of the tables that discuss the other tutorials that are available. So just be aware that if ply number optimization is not your only objective, if you want to optimize the shape, there are other tutorials for that. But in this case, we are assuming that our plies are fully continuous. So we're only interested in performing the ply number optimization. So let's go ahead and jump out of here. And now I really have not rehearsed this. So this might be good for you because you get to see me make a lot of mistakes. You get to see me try to troubleshoot all the mistakes. So this is a very honest tutorial, if you will. Now, here we are at the web app. What we need first is the bulk data file for this example. I'm assuming you've already created your model. You've already created the mesh, your materials, your loads and boundary conditions and things like that. And so here, that's what we have. We go to the ply number optimization tutorial. We click on starting BDF files link. And then if we look inside of this bulk data file, this is pretty much ready for us. We've already performed a test analysis. We've defined our two laminates, PCOMP1 and PCOMP2. You can see the 18 layers for both. We're ready to configure our ply number optimization. So let's go ahead and jump back to the home page. Let's open the optimization for Soul 200 web app. So this is where we start configuring our ply number optimization. So let's go ahead and take that bulk data file. Let's upload it to the web app. Now, there's a lot you can select here. These are all the thicknesses for the PCOMP entries. Now, I'm only focused on the super plies. So what I can do is look for that number 0, 2. So here are the super plies. If you look at one thing in the PCOMP entry, the super plies all have a thickness of 0.02. So 0.02 here and here. Here I go to the table, I look for thickness. I get all my PCOMP thicknesses here. Here I look for 0.02. Now I have all those super ply layers in this table. Now what I do here is for the 45-degree layers, I click on these plus icons. Let's go ahead and do this for PCOMP 1 and 2. I select all 45-degree layers. And now here, I have the thickness variables for the 45-degree layers. Let's go ahead and create one ply number variable. So here we'll go ahead and say that the lower bound is maybe 2. The upper bound is maybe 100. And then the initial bound, we're going to start the ply number optimization with 2 plies, if you will. Let's go ahead and turn on the label comments column, and let's call this ply numbers for a positive, negative 45 degrees. Now we've created our ply, or rather our variables for the thicknesses of the 45-degree layers. We've created one ply number variable, y1. Now we have to connect the thicknesses with the ply number variable. So here I create a D-link. I say that the first thickness is equal to the product of y1 times 0.005 inches. So now the optimizer is going to be modifying the number of plies. And then this is going to cause the thickness of the layers to be updated. So that's what I've done here. Now I've done this for the 45-degree layers. Let's now repeat this for the 90-degree layers. So here in the row, or in this table, we select this row, and anywhere else where we see 90. And now I have these additional layers. Now, one thing I forgot to do is I forgot to do this for the other thicknesses. 6, x7, x8, and I think it was up to x8, right? So the first 8 variables are for the 45-degree layers. So here what I said is that variable x1 through x8, they're all equal to the ply number variable times the thickness of one ply. And now we'll go ahead and repeat the process for the 90-degree layers. So we start off with 2 plies. The ply number variable is allowed to range between 2 and 100. If the upper bound or the lower bound is not to your liking, you can make the adjustments like I'm doing here. Here, this is the ply numbers for 90 degrees. And then like before, we'll create a new D-link entry. We'll say that variable x9 is equal to the product of y2 times the ply thickness. And then here we have x10, x11, x12. And now the last group, which are the 0-degree layers. So we'll go ahead and click on these remaining layers. You'll notice that we have 4 new thickness variables, x13 through x16. One quick comment, as you create your variables here on the right, you get the respective bulk data entries. So here, this is a good way of learning how all these entries are associated with each other. You have your desvars, your D-links, your ply number variables, and so on and so on. Here, I've created my thickness variables for the 0-degree layers, and now I'll create a D-link that associates x13, x14, x15, and x16. And another thing here, if you manually do this, if you take all of this, let's go ahead and copy this to a text file. If you try to do this by hand, you will make mistakes. Those mistakes will cost you. They might cost you days, weeks, maybe months of work trying to fix all those errors. Here, the web app tells me exactly where the error is. Anytime you see a red icon, that's an error. You have to fix that or your optimization is going to fail. Here, I get told that there is an error in this input. Variable y3 does not exist, and that's because I forgot to create variable y3. Let's go ahead and create that variable now. So this is a new variable y3. It ranges between 2 plies and 50 plies. And then here, let's go ahead and add a description. So now if I go back up here, that error is no longer here. So here, let's suppose I made a mistake and I typed in y31. Y31 doesn't exist. Here, the status is red. There's an error. If I try and run this optimization, it will fail. Let's suppose I continue on with my work. I totally forgot about it. When I go to export, I get told exactly where the error is. So here it tells me, hey, you made an error in the variable section in step 3. Click here. It jumps to the table. It tells me that the error is here, and great, perfect. I know where the error is. I fixed the error. I continue on with my work. Remember, if you do this by hand, you're going to have so many errors. You're going to spend so many hours, days, and weeks. Don't save yourself the trouble and the time and the stress. Feel free to use the web app. Now, let's go ahead and quickly look at what we did. We created our various thickness variables, x1 through x16. And let me make sure I've done this correctly. Yeah, I'm sure it's been done correctly. We've created our 3 ply number variables. We associated the ply numbers to the thickness variables with these D-links. Now, one thing, let's do a check. Let's go to the objective section. Let's create our objective to minimize the weight. So here I have this big table of responses you can select from. Here the first response is weight, so I click the green button that sets this as a objective. Here I want to minimize this objective. Now, if this is truly configured properly, this is what we should expect. Let's suppose that the number of plies starts with 40. We expect the optimizer to reduce the variable to 2. And I'll explain why in a moment. Let's go to the exporter and click on download PDF files. Now, our ply number variables are starting at 40. If we look inside the bulk data file and we go to the ply number variables, you can see that the X init field, that's 40. We only want to minimize the objective. There are no constraints. So what is the optimizer going to do? Simple. I just reduce the number of plies. I reduce the variables y2, y1, y2, and y3 as much as possible until I hit the lower bound of 2. So this is a useful check because it lets us know whether or not we're doing this properly. Here we're done with the results. Let's look at the objective. We minimize the objective with no constraints. You notice that for the constraints, we get NA, not available. There are no constraints to report. Here we get a legend. Let's go ahead and turn off everything and turn on only the ply number variables. We started with 40 plies and we went down all the way to 2 plies. Perfect. So this is what we were expecting. Our first optimization was successful. Let's now add the constraints. So here, let's go ahead and change our initial values to 2. Now, if you're performing ply number optimization, I recommend setting the initial value to the lower bound. So here, our lower bound is 2 plies. Start with 2 plies. Your laminate is going to be so thin that is going to be violating your ply stress, ply strain, or failure index constraints. That's okay. What you're going to see the optimizer do, it's going to increase the number of plies until it satisfies all the constraints. You could start off with a bigger number, say 50. But from experience, I've noticed that this tends to yield suboptimal solutions. I found out that the best approach is to, just start off at the lower bound. Now, this only applies to ply number optimization. If you're dealing with other problems, I have some other comments in the other tutorials that you'll see me make. Okay, let's go ahead and move on to the constraints. So what we're going to do now is we're going to look for C, failure. You'll notice that here I get some other responses I can constrain. I can constrain the failure indices for the plies. I can constrain the ply stresses, or I can constrain the failure indices. So here, let's go ahead and look for maybe failure if you want, or C failure like I do here. Let's go ahead and create 8 responses or 8 constraints. 1, 2, 3, 4, 5, 6, 7, and 8. Now let's configure one constraint. If we look back at the presentation, let's go ahead and define a constraint for layer 1. So this would be one of the most outer plies. And we're going to do this for both PCOMP 1 and PCOMP 2, so left and right. So let's do that now. So we are going to constrain any element associated with PCOMP 1 and PCOMP 2. So PCOMP 1 and 2. The upper limit, it's not going to be 1. It's going to be 0.95. And the reason I'm using 0.95, if you use an upper bound of 1.0, sometimes the max failure index is 1.01 or 1.05 or 1.001. sometimes it exceeds the upper bound by a small amount. You could use a value of 0.98. So then your values are maybe 0.98999 or 0.981 or something along those lines. But here, just to be sure that I'm less than 1.0, I use 0.95. You can use 0.98 or 0.97. It's really up to you to decide. So here I've said constrain the failure index for PCOMP 1 and 2, make the upper bound 0.95, specifically constrain the failure index for layer 1. Now I have to do this again and again for the other ones, so layer 2, 1 and 2, but there's a faster method. If I go to options, click export, I get a CSV file that I can open in Excel. I can go ahead and define that here. And you might be asking yourself, why not just do this all in Excel? If here I'm making the edits in Excel, why not just do this with Excel? Now, the reason is because Excel does not check for errors. Excel does not know anything about Nastran, but the web app does. Here you can see that rows 3 through 8 have errors. You look at the status column, they're all red. It detects errors. I'm missing inputs in these input boxes. Excel does not track that. So if you use only Excel, you're going to get a lot of errors. So here, we're only using Excel to create these entries really quickly. And let's go ahead and see what the layer numbers are. So I think the top layers are, let's go ahead and see here. So layers, right now we've defined layers 1, 2, 3, and 4. Now we need layers 18, 17, and I think this is a typo right here. 18, 17, 16, and 15. Let me make sure this is all updated. Oh, yep, that should be 15 here. 1, 2, 3, 4, 15, 16, 17, 18. So what we're going to do here in Excel, this column ATTB, this is the layer number column. So this is going to be layer 17, layer 16, and layer 15. So layers 1 through 4 are the bottom 4 plies, and then the top layers are the 4 top plies. Layers 18, 17, 16, and 15. Let's go ahead and save this file. Click yes. Let's go here. Let's go ahead and import that CSV file. Click import. Let's close this. Now, this table should be green. It tells you everything was imported properly. And if I look here, all the other input boxes have been updated for me automatically. So if we look here, columns property, ATTA, ATTI, even the upper bound column, these should all be identical. Only column ATTB should be a little different. We are constraining the failure index for the bottom plies, 1, 2, 3, and 4. And we're constraining the failure indices for the top plies, 15, 16, 17, and 18. Now, we're done configuring the constraints. Let's go to the subcases section. Now, this is the part that takes a lot of time, but here in the web app, you can just simply mark all the checkboxes. Here, what we're doing is we're assigning the failure index constraints to subcase 1 or load case 1. You can go checkbox by checkbox, or you can click on this green button and assign some constraints to all the visible subcases. If you wanted to, you can customize it to your liking. I know for more complex problems, you're going to want to customize which constraints go to which subcases. And now we're done. Let's go ahead and download those new set of bulk data files. And now one comment here. Let's go ahead and change this file name to 1. Now, some of you might be students who in maybe 5 or 10 years are going to learn how to code. Generally, you don't want special characters in your file names. So a moment ago, our directory was going to have this naming convention: spaces, parentheses, question marks, special characters in the directory names or file names, these typically cause problems. So I typically do not use spaces. I do not use special characters in the file names. That's why I removed the parentheses. And then I started the optimization. Let's go ahead and see what's going on here. If we look at the F06 file, the very bottom of the F06 file gives me the confirmation of whether or not the optimization was successful. Here we get a good message, run terminated due to our convergence. This means that the optimization was successful. Here we get an update of the history of the optimization. Here I see that the constraints, the first normalized constraint was positive. That means I'm exceeding one of the constraints by here 3.83 or almost 400% or 383%. That means that first laminate with 2 plies for each layer, that is violating the failure indices. But here it's trying to reduce, or not trying to reduce, it's trying to make that worst case failure index negative or close to 0. Here in design cycle 3, it's telling me it's negative 0.08. Negative means you're satisfying your constraints. Here in the last design cycle, it's negative. If it's negative or very close to 0, you're satisfying your constraints. Here, since the initial design was violating the constraints, it had to increase the number of plies. That's why the weight increased. But then it was able to reduce the number of plies towards the second part of the optimization. Now let's look at the ply number variables. Here we look that we started off with 2 plies, and then at the end we ended off with 2 plies for the 45 and the 90-degree layers. And then for Y3, look what's going on with Y3. It's ending with 7.5 plies. Wait, but I wanted integers for my plies. I wanted either 7 plies or 8 plies. Here, what you can do, you can just round it if you want, but Nastran has a built-in way to land on specific integers. If we go back to the web app into the variables section, here in this column, allow discrete values, you can type in those values, 1.2 or 1, 2, 3. You're going to tell Nastran, hey, you know what? Land on these integers, 1, 2, 3, 4, so on and so on. You would need to type this out all the way to 50, but this is too tedious. There's a way to do this a lot faster. Use the through by method. So here what I'm saying is that, hey, land on values between 1 and 50, 1 through 50, in increments of 1. So then we copy and paste this to the other variables, and let's rerun this optimization. Let's go ahead and download this again. And remember, if you do this by hand, you're going to go through a lot of errors. So when possible, try to use the web app or some other similar tool to do this a lot faster without errors. Now, this next optimization, we told the optimizer, hey, do not land on fractional values for the ply numbers. Give me integers. Give me 7 or give me 8. Nothing in between. So here, it's going to be the same optimization, but something special happens at the end. So here, it increases the weight and then decreases the weight. The failure or the normalized constraint is originally 3.83, but then you see by the end, I get negative. So that's a feasible design. But here, let's look at the ply number variables. Here in design cycle 6, I get 7.5 for variable Y3. Now, a new additional design cycle is performed. This is the discrete design cycle. Here, if you look closely, my variable number is now 8 and 2. So here, what's happened, generally, Nastran has performed a rounding operation. Now, it's not exactly rounding, but you can think of it as a rounding procedure. Here, it's taken that fractional value of 7.5 plies, and it's moved the value to 8 plies. Perfect. I'm done here. Now, let's look at a few final things. Your updated PCOMP entries are going to be in the punch file. PCOMP 1 and 2 are identical. Let's go ahead and copy the first PCOMP. Now, what I'm going to do is I'm going to split this entry. You can format it like this, but I'm taking a big liking to this other format. You just define one layer per row. This is what my updated PCOMP entry looks like. Let me move this to the right. And here on the left is my old PCOMP entry. You notice that the thicknesses for the super ply layers are 0.02. The new thicknesses are 0.01 and 0.04. Great, perfect. So what can I do now? I need to update that original bulk data file. So you can do this. You can say, copy that file and call it maybe one manually updated. So let's open that file. And what I'm going to do is the following. I'm going to take those old PCOMP entries and I'm going to delete them. And then here, I'm going to copy this here and put it in the original location of the PCOMP entries. Okay, and then save the file. Great, perfect. So what I've done here is I've taken the new thicknesses of the laminates and I've copied them over to my original file. And now this file has the updated thicknesses. Alternatively, there is a file here or directory called workspace B. This file has this done automatically. So if we go to the PCOMP entries, you'll notice that the thicknesses are 0.01 and in this case it's a 0.04. I forgot to mention that Nastran does not use the discrete value. You notice that here the value is 0.037533, but the actual value is 0.04. So you see that it didn't update the punch file properly, or at least this PDF file. So there's one other thing we need to do here that I did not discuss. These layers are still super plies, but we don't want that. We want layers that are plies. So what I need to do is I need to manually split these plies. So we know that for the 45-degree plies, there are 2 layers. And then for the 90-degree plies, it's the same thing. There are 2. And then for the 0-degree, I think there were 8. So we have to go ahead and duplicate this 8 times. 1, 2, 3, 4, 5, 6, 7, and 8. And then we have to do this for the other mirror side of the laminate. That's too tedious. What the web app did, it created a new file for you, if you will, this punch file. This punch file includes the same PCOMP entry, but all the plies have been automatically created for you. So here, if we look at this laminate, you can see that all the thicknesses are 0.005 inches. Here I have 8 plies for the 0-degree layers, 2 plies for the 90-degree layers, 2 plies for the negative 45, and 2 plies for 45. And this was done automatically for these PCOMP entries. Now, what you can do is you can go ahead and take these entries, you can copy them, and replace the old ones if you wanted to. Now, this method of manually updating the entries, this can get very tedious if you had 50 PCOMP entries. There's actually a faster way to do this. If you go back to the optimization web app, go to results, go to the PCH to PDF web app, you can pick that PCH file, that punch file, pick your original bulk data file. This is going to swap those old entries with the new entries. Here on the right are the old entries. Here on the left are the new entries. So what I'm going to do now is click download. I'm going to get a new directory here. I'm going to call it maybe 3. I'm going to download this, or extract it rather. And if I look in here, that would be this file here on the left. If I zoom out a little, you're going to see that my PCOMP entries have been updated for me automatically. Great, perfect. So now what's there left to do? Let's go ahead and now look at these different versions in the web app. So let's go ahead and do this. Let me make a modification to my operating system. Maybe we want to look at what the thicknesses of these different examples look like. So what I'm going to do is close some of these other tabs. I'll leave this tab open, close that one. Let's go ahead and upload the bulk data file to the viewer. Now what the viewer is, it lets you look at your finite element model in the web browser, and later on we'll go ahead and look at some results. So what I'm going to do is I'm going to upload the original PCOMP entry, or original model if you will. Let me close this. Let me close this here. I'm just going to close some of these other applications so we're not bothered too much by all of these windows. And let me do this for these other windows. Let's go ahead and close some of these. Okay, so we selected the original bulk data file. This is what the cylinder looks like. Let's go ahead and look at it from this view. Let's zoom in very carefully. So right now what we're looking at is the nodal plane where we have all the nodes and the 2D elements. Now, the reason I'm zooming in very carefully is because you can actually display the thicknesses of the laminate. So let's go ahead and do that right now. And let's zoom in a little, or zoom out. So each layer gets its own color. Maybe you don't want that. You want all the 90-degree layers to have the same color, or the 0 degrees layers should all have the same color. Let's click on this button under color of detail. And now we know the following. The core is beige. The 0 degree layers are gold. The 90-degree layers are red. The negative 45-degree layers are green. And the positive 45-degree layers are blue. So this is what the original laminate look like. Let's look at the laminate after we perform the ply number variable. And remember, the optimizer has only modified the thicknesses of the layers. It did not add plies or remove layers. It only modified the thicknesses of the layers. So here, like before, let's go ahead and look at what that PCOMP entry looks like. And I think it might be worth displaying what the PCOMP entry looked like. Let's go ahead and open up that file. I think it might be worth showing these side by side. Let's go ahead and say yes here. We want to open this file. Okay, just bear with me while my virtual machine catches up. Okay, so here on the right, let me make sure I got this right. Okay, let's move this to the, here on the left is the original bulk data file. Here on the right is the new bulk data file with the new PCOMP entries, and let me reformat this. So this is before ply number optimization and after ply number optimization. Notice that both PCOMP entries have 18 layers defined. Remember, the optimizer is not going to insert layers. It's not going to insert rows to the PCOMP entry. It's only going to optimize the thickness of each layer that we specified. So before we had thicknesses of 0.02, but now we have thicknesses of 0.01 and 0.04. Notice that the thickness for the 0 degree layer is 0.04. It's thicker than the other layers. So here in this first window, that is the original PCOMP entry, the original laminate. Here is what the updated PCOMP entry looks like. So let's zoom in and let's turn on the wireframe and let's turn on the thicknesses. And let's change the color. So you'll notice a few things here. If you look at the blue, the green, the red, and the gold rows, those all have the same thickness of 0.02 from the PCOMP entry. But now let's look at the new thickness of the PCOMP entry. The new thickness is as follows. The blue has 0.01 inches of thickness, green has 0.01, red has 0.01. The gold color has 0.04 inches in thickness, which matches the thickness that we define here in the PCOMP entry after the optimization. But now let's look at the final bulk data file. Remember, at the very end, we took that PCOMP entry and we sliced it. So let's go ahead and open the BDF file. And while that's happening, let's go ahead and actually upload this to the web app. So I want to show you the differences between these different PCOMP entries. That's what I'm doing right now. So let's go ahead and jump to directory 3 and upload that bulk data file. And then we're going to go ahead and zoom in very closely. While that's happening, here on the right is that slice PCOMP entry. So this is where you see now we have multiple layers where each layer is one ply. And we know this because of thickness. So as an example, for the 0 degree layers, all these plies were combined into one layer of 0.04. So that would be this layer. But then after that, we split it into, I believe, 8 plies. And remember, the ply number optimization told me I need 8 plies for variable white 3. So let's go ahead and look at this laminate in the viewer. So let's go ahead and maybe change the color, zoom in. And let's go ahead and turn on some of the wireframe. And let's zoom in a little bit more. And let's go ahead and turn on the thicknesses. And let's change the color. Perfect. So now you see the difference. This was before optimization. We only varied the thickness of the inner layers. This was the result after. And here had a lag a moment ago. Here the thicknesses of the inner layers were modified, so before and after optimization. But then we needed to split the PCOMP entry into different layers for the plies. So this was before the split and then after the split. If you count, now you have 8 0 degree layers, 2 90 degree layers, 2 negative 45 and 2 positive 45 degree layers. And then whatever happened at the top also happened at the bottom. Now let me close all of this. And now let me mention one thing about this tool. Some of you might go on to work on aircraft or ground vehicles. You're going to have hundreds of individual components, millions of elements. Sometimes you need to be able to look inside the model. And we have an option here called first person mode. Let's go ahead and jump into that mode right now. Here, first person mode lets you look at the model like you would in a video game. Here I'm moving inside of the cylinder, and now I am inside of the cylinder. Here, if you think about it, maybe this is the fuselage of an aircraft. you need to jump inside the fuselage and look at some of the stiffeners, some of the deck, the beam elements, the 2D elements. You need a way to do that, and the way you can do that with the web app is in first-person mode. So I wanted to point that out. And now let's talk about results. We need to look at whether or not the failure indices are truly less than 0.95. So this is what we're going to do. During the optimization, there was a H5 file that was created. That H5 file contains the displacements, it contains the failure indices during the optimization. So what I'm going to do now, I'm going to take that file and upload it to the web app. So let's go ahead and jump to the web app, or jump to that directory and select that H5 file. Let's click open. Let's click upload. Now, let's make sure that the final failure indices are within 0.95. So let's go ahead and give us a moment to load. Right now I'm looking at the displacements. I don't want that. I just want to look at the failure indices. So what you do is you select this data set, element failure index quad 4 comp. And let's do this for the final design cycle, subcase 1. Now all the 5 load cases or 5 subcases, they're all the same. I use the same pressure load for 5 load cases. So the results for one is the same for the others. Let's go ahead and scroll down. Once you select the load case, let's go ahead and select the layer. So remember, we only care about the outer 4 layers. So these are the failure indices for the outer 4 layers. So here selected layers 1 through 4 and 15 through 18. Right now we're looking at the maximum failure index, and this is what we have. We see that the max failure index is 0.9438. Perfect. So 0.9438 is less than 0.95. This is a feasible design. So the optimization was successful. We're less than 0.95. Now, if we look here in the local optimization tool, you get these normalized constraint values. These are not failure index values. These values here do not have values of inches, meters, PSI. No, these values are unitless. But these values, these normalized values, are derived from the original constraint values of failure indices, ply stresses, in inches, and so on and so on. So what you can do is the following. You can take the F06 file. The F06 file has information about the optimization. So here, let me scroll through this file. Here it gives you information about what the weight is. So here, this is the weight or the objective. It gives me information about the failure indices. Above that, it gives me tables about the normalized constraints. So as the name implies, those constraints have been normalized. They are now unitless. So what you have to do is you have to take these normalized constraints that I'm highlighting. You have to manually associate them with these responses. You can do this with Python or with Excel or with the text editor. But what the responses web app does, it does the association automatically. Here, that same data has been combined together. So in the value column, I get the actual failure index value for different elements. Here on the left and right hand side, I have a normalized constraint column. The lower bound and the value column are combined to yield a normalized constraint value for the lower bound. The upper bound and the value is combined to yield a normalized constraint value for the upper bound. So this is done for you automatically. What I'm interested in is in looking at the maximum normalized constraint for each design cycle. Here, the first normalized constraint is 3.83. So here in this table, I look for that value, 3.83. Here in the first row is 3.83. This is corresponding to response R3. It's a failure index constraint. Here I click on show more information. I get told that this is for design cycle, or for the initial design cycle. I get told that it's in element 144, component 5, the failure index for laminate 3. So let's do a confirmation. Here, I'm going to select the first load case. Actually, what load case was it? Subcase 1. We look at the subcase column, subcase 1. We look here, we look for subcase 1 for design cycle 0, which is the initial design cycle. And then we are going to go ahead and find the failure index for all these different plies, if you will. So it's going to be gray. And the reason it's gray is because you need to select both a failure index or a component and the plies. So here we'll go ahead and select plies 1 through 4 and the last 4 plies. So these are the 4 plies for the top and bottom. So here I'm pressing and holding the control key and selecting different rows. And now let's turn on my max label. So here we get told that the highest failure index is in element 144, layer 3. This is the same value that's reported to the optimizer. So what this plot is showing you, it's showing you the worst case constraint. So you need to look at this table and look at, okay, what's going on here through each design cycle. At the very end, we get told which constraint is the worst case constraint. We are told that it's 0.9438. And if you recall, this was for load case 1. So let's go ahead and jump to load case 1. If you remember back maybe 5 or 10 minutes ago, 0.9438 was the same value we saw a few moments ago. So just to prove to you, let's go ahead and look at that real quick. So again, it will be gray at first, but let's go ahead and select the component or the field, failure indices, the top 4 and the bottom 4 plies, and then let's turn on the label. So we get 0.9438 as expected from the F06 file. So again, all of these tables that you see here, these are the values the optimizer looks at during the optimization. We were able to use the responses web app to quickly get some information about what's going on with the failure indices during the optimization. Okay then, so let's go ahead and maybe close this. And let's do a few last things. We want to perform a quick stacking sequence shuffle on the stack. So I'm going to go to the full list of web apps and click on the stacking sequence. Let's go ahead and take that bulk data file. Let's upload it and let's select one of the PCOMP entries. So we'll select PCOMP 1 for now. And now this is where I can do shuffle these. For example, say I want to alternate the sign and pair the 45-degree layers. I can go here and say pair. Maybe you want the sign to be the same. Let's go ahead and perform the optimization. And then after the optimization, so notice that at the top is the original stack. And then here we have the new updated stack. We have 45, positive, negative, positive, negative. The sign is the same, positive, negative, and they are paired. But there are a few odd things about this. Sometimes the core layer will be moved. Maybe the 0-degree layers, there are too many that are close together. So we have to fix some of these layers, if you will. The 90-degree layer, maybe you want to fix that in a specific slot or layer. I'm going to move it down one layer. I'm going to fix these 4 layers. I'm going to fix the core layer. So those fixed layers, they are going to stay where they are during the shuffling. So this is my new updated result. You'll notice here that I have a lot of 0-degree layers that are together. Maybe you say, you know what? I don't want all these layers together. So maybe you say, you know what, I want at most 4 0-degree layers, or rather you want at most 4 consecutive 0-degree layers. So I type in 4 in this table, click perform optimization, and now I have a better result. But then you say, you know what, I want the 45-degree layers to be distributed a bit more continuously throughout this laminate. You can use this other table. You could say maybe I want at least one 45-degree layer every 5 layers. And so you get a different result. So now you can see that the 45-degree has been embedded here. So there are different rules that are supported in this tool. Here, let's go ahead and save these entries. There are a few additional things. You can go ahead and display more columns. You can toggle the plies. You can toggle, if you have multiple PCOMP G or PCOMP entries, you could change the visualization to your liking. If we download this, let's go ahead and look at what the new result looks like. So let's go ahead and rename this 4. And let's go ahead and open this in Notepad. Let's move this to the side. So here on the right is going to be the laminate after we modified the sequence. Here on the left, let me see if I can find it here. This was the original PCOMP with the original sequence. So you can see that a lot of the 0-degree layers were consecutive. But here on the right, notice that the sequence has been updated. And that's because we went ahead and performed a stack and sequence optimization in the web app that you saw a moment ago. So one quick thing about this, notice that we did not do this for PCOMP 2. You can also do this for PCOMP 2. You go back here, you select PCOMP 2, go to optimize, use the same rules that we used a moment ago. I forget exactly what they were. I think there was something like 1, 5. This was yes, and this was same, performed, and then you have to fix the plies. You could use the same rules there, or you can do this. You can just copy those same rows and carry those over manually. It's really up to you to decide how you want to update your PCOMP entries. And I just showed you one example that you could do. You could either do it manually or you can do it within the web app. So now let me start wrapping this up. That is how you perform a ply number optimization. I know that there was a lot that I discussed. The reason I wanted to discuss a lot is because a lot of this information is in parts. It's in pieces. It's distributed across all these different tutorials. I wanted to combine all of that information into this one ply number optimization so you can see all the pieces that I need to consider for a ply number optimization. There's one last thing I want to do. You can either pause or stop the video here and try your own ply number optimization, or you can continue on. Let me go ahead and modify these files. So let me move some of these files. Now let me actually copy all of this. There is one option that I wanted to point out. So here, if we look at the original bulk data file, let me close some of this. If we look at the original bulk data file, we explicitly defined all the layers in our PCOMP or our laminate. There is a shortcut to doing this. Let me create a new bulk data file called sim. So here's the same file, except we append sim to the file name. And let me make sure I give it a file extension. Let's go ahead and click open. Here, what I'm going to do is in field 9, I'm going to give it lam equals sim. use, or rather, I've defined X number of layers that define one half of the laminate. Nastran will internally create the second half, the second mirror half of the laminate if you use the sim option. So here, let's go ahead and delete the other half of the laminate. And let's do that for the second PCOMP. So here's sim. Let's delete that laminate. So even though I've defined, I think 8 layers, 1, 2, 3, 4, 5, 6. Oh, I'm not counting right. So it's 4 is 8. Oh, right. So here, even though I've defined 9 layers here, Nastran internally knows that there are 18 layers. So you can think of the sim option as like a shortcut, a faster way to define your layers if you have a symmetric laminate. This has implications when you create your design variables. So here, let's go ahead and go to that optimization. Let's also modify the bulk data entries here. And let's go to sim here. Now what's happened is that I'm using the shortcut here, so I only need to define half of the layers, and then Nastran builds the other half. If you want confirmation, you can go to the viewer web app and upload it. So let me go ahead. So let me upload that bulk data file. Again, even though I've defined 9 layers, Nastran will automatically build the other 9 layers. Here, I'm going to upload that same sim file that has 9 layers defined. And you'll see that when we display the laminate, we will have 18 layers because we use the symmetry option. So here, let's go ahead and look at it from this orientation. Let's go ahead and zoom in. So here, we've only defined maybe the bottom half, and then the second half was automatically built for me. So this is what Nastran is doing again. We built half in the PCOMP entry, Nastran builds the other half. Now, what I went ahead and did, I took the optimization files and I manually updated the PCOMP entry. Now, let's go ahead and try to perform this optimization. I expect the optimization to fail, but let's see if it works. I forgot to delete my old result files, so let's go ahead and do that right now. So let's go ahead and delete everything but the PDF files, and let's go ahead and start MSC Nastran. I got a failure, so let's stop here. Let's look at the error message. User fatal message. dvprel specifies property name T13 that is not specified on PCOMP entry 1. So what's happening here? Let me go back to the presentation we had a moment ago. So that would be this presentation. Let's go ahead and jump to this section here. So what's going on here is that we only define half of the PCOMP entry. So the PCOMP entry does not have, at least on the front end, it does not have these layers. But we explicitly define thickness variables for those layers. So Nastran failed because, hey, you wanted to optimize the thickness of layer 14, but guess what? PCOMP 1 and 2 do not have layer 14. So this is what we have to do. We have to delete those thickness variables. And so let's go ahead and do that now. Let me go back to the web app. I'm going to upload those optimization files. And let's go ahead and select those files and upload them. So we don't need to define those other thickness variables for the undefined layers. So if I look here, fortunately, we know which ones those are. Those are the ones with no description. So what we're going to do, we're going to delete that thickness variable, and I guess I can't delete that because there is no PCOMP entry for that. So this is what you would do. You would either need to redefine your thickness variables, or you would go ahead and manually modify the entries. Here, maybe it's easier if you just restart the optimization, so that's what I'll do here. It might be worth looking at this again. So what I'm going to do is I'm going to take that bulk data file from before, and let's quickly build this out. So thickness 0.02, and let's go ahead and look for, let's go ahead and do this with a 45. We'll create a D-link. We'll say that X variables 1, 2, 3, and 4, they're associated to this variable. We'll go ahead and do this here, 2, 2, and 50, 1 through 50 by 1.0. And then this is going to be the ply number variable. Ply numbers for positive and negative 45 degrees. So let's go ahead and create my other ply number variables. And this next one is going to be 90 degrees. Next one is going to be 0 degrees. Let's go ahead and do that here. And now we've done this for 45. Let's do this for the 90 degree layers. Let's go ahead and do that here. So x5, x6, they're equal to y2 times 0.005 inches. And let's do this for the 0 degree layers. So these two. You notice that we're dealing with half the thickness variables. So x7, x8, y3 times 0.005. Make sure everything looks good here. Go to the objective, click on weight, minimize the weight. Now for the constraints, we'll go ahead and create 8 failure constraints. Now, you'll notice that the number of dvprel and desvar entries, the number of dvprel entries is 8, but before it was 16. That's because now we're using the symmetry option. Whatever we do to one half of the laminate happens to the other half of the laminate. So that's why we don't have to define 16 thickness variables. We just needed to define 8 thickness variables for one half of the laminate, and then everything else is done for the other half of the laminate. But we're still working with 19 or 18 layers, if you will. So we still need to constrain layers 1, 2, 3, and 4, and then layers 18, 17, 16, and 15. Now what you can do here, you can just take that same CSV file from before and you can just upload it. So now if you look here, I'm still dealing with an equal number of layers. Layers 1 through 18. Here I've only constrained the outer 1, 2, 3, and 4, 15, 16, 17, and 18 layers. For the subcases, let's go ahead and assign all the constraints, and now we can perform the ply number optimization. And so we should get the same solution at the end. So let's go ahead and rename this maybe number 2. And again, the reason I wanted to do this is because I know some of you, you might be aware of the symmetry option. You might be using the symmetry option in your PCOMP. So I wanted to detail how to take that into account when you set up your ply number optimization. So what do we expect? So before we expected 2 plies for the 0 and 45 degree layers, or for the 45 and 90 degree layers, we expect 2 plies. And then for the 0 degree layers, we expect 8 plies. And that's what we get. We get the same solution. And then everything we said for the previous discussion applies. So the final PCOMP entry has to be updated. Right now it's including these super plies. Notice that we only defined half of the laminate. The symmetry option triggers Nastran to define the other half of the laminate for us. Notice that we get thicknesses of 0.01 and 0.04 for the super plies, but then we have to manually split this, and that's done for us in this PCH file. So here, what do? We could take this file, we could take these entries and update the old bulk data files. And notice here again, we've only defined half of the laminate. The other half is automatically created by Nastran. So that was the last thing I wanted to leave you off with. What do you do when you have the symmetry option? At this point, you update your bulk data files. You could look at your final failure indices and so on and so on. Everything that we did in the first part applies to the second part. And now that's pretty much the end of the tutorial. Like I said before, this is the most commonly asked question. How do I configure a ply number optimization? So I wanted to take time to build this tutorial. I wanted to show you a fair amount of complexity. I wanted to show you what happens when you have two PCOMP entries you want to optimize. I wanted to show you what you do when you have multiple load cases. Some of you will have different constraints for different load cases. So I wanted to show you what the process is like for that. I wanted to keep it simple. At the same time, show you these complex tasks with optimization. Now, everything you saw here, you could do by hand. If you're willing to spend weeks of training, if you're willing to spend weeks of debugging errors, you can do this by hand. But some of us, unfortunately, don't have all this time to afford for this. You saw how I was able to quickly set this up in the web app. If there's ever a problem, I get an error message. I know exactly where the error is. So here, let's go ahead and purposely make some errors here. And let's maybe shuffle this table a little. Let's shuffle this table a little. So if you look at these tables, everything looks blue. Everything looks okay. Everything looks okay here. I go to download my bulk data files. And let's do that right now. Let's see what happens when you miss some of these errors. Let's rename this 3. Let's extract the contents and let's run Nastran. I expect there to be errors. And this was on purpose. You saw me purposely make those errors. I get a fatal message when I run Nastran. Now I have to go through all these different fatal messages. I have to fix all of these fatal messages. And a lot of the time, we don't know how to fix these. We have to really interrogate this file for more information. But now with the web app, here I get exactly told where the error is. I click on this link. Oh, there's an error here. Let's go ahead and delete that. There was a mistake there. Let's go back to the exporter. Oh, I get another error. Let's go here. Oh, I forgot to type in the PCOMP IDs. Okay, everything looks good. Let's re-download these files and let's try again. Now, I'm not saying this is going to catch every possible error. This is going to catch some of the most commonly found errors. This is going to save you a lot of time because, again, you could do this all by hand, but it's going to take you weeks of study, experience trying to fix those errors. It's going to take you weeks of building your own in-house tools. And again, we don't have time to go through all that. We need to do the work as quick as possible. And here you saw that with the web app, I was able to quickly build my optimization, quickly fix any errors, and get what I wanted, an optimized model. So that's pretty much the end of this tutorial. I hope you found it insightful. If you have any questions, you're always welcome to contact me at this email address. I would try to get back to you as soon as possible. So with that, I'll stop here. And as always, thank you so much for watching.